First speaker for this afternoon, Angelica Osorno.
First, I would like to thank the organizers for inviting me. Those of you who know me a little bit, I don't do much traveling these days for various reasons that maybe are 5 and 1 years old. So when I say yes, it means that I really want to be here. So take that as a thank you, but also a sign of appreciation. I've been having a lot of fun this week in particular, just seeing people that I don't see that often and meeting new people as well. So today I'm going to tell you about equivariant operads, multiplicative structures, and transfer systems. And it's I was talking to Marcus about titles this morning, and it's just like, I have to tell you the things that maybe I'm going to talk about today when I submitted an abstract at some point. And when you submit an abstract, maybe you just don't know what you're going to talk about. And so just throw a lot of words in the title, but I'm actually going to talk about all those things today. All right. Again, those of you who know me, you probably know that I like giving talks with a lot of background. And this week I had conversations with some of you about like struggling with the fact that Mike had given all the background that I would usually give in this talk. Thank you, Mike. But then I decided that I was still going to give the same background because it doesn't hurt to hear things twice, like I tell my students all the time. I want to start really, really basic, kind of thinking about what we mean when we talk about operations up to homotopy. And so if we go all the way back to the 70s and the 80s, we start thinking about, okay, well, if I have a strict associative operation, what does it mean to say that it is associative up to homotopy? And maybe you think right away about A infinity and Stashev's work, but then you realize that Stashev's work actually has a lot of like different pieces, and you can have A1 and A2 and A3. And that means that maybe you're only associative up to homotopy, but maybe you're associative up to higher homotopies, right? And you actually get different answers depending on what you want. And I think this is part of the story that we need to remind ourselves that we're telling here, is that we have choices whenever we say up to homotopy. And in the case of associative, maybe we mean A infinity, which is up to all higher homotopies, but maybe we want to stop at AN for some specific n. And the idea of choices is something that is going to kind of be recurring in my talk today. Now, when we move to commutative, maybe we go straight to A infinity, but also maybe we stop at E2, E3, and so on. And maybe you're realizing that E1 isn't there because E1 is the same as A infinity. And then the talk today, and this is the beginning of the talk, is going to recap the story that Mike was telling us in the first couple of lectures, is what do we mean by G commutative up to homotopy? And so I want to start really, really, really basic, thinking just in sets. So here I'm going to have, and I don't know how to get rid of that menu that is blocking the fact that for me today, G is a finite group. And so when I talk about G commutative, maybe I'm just in spaces or maybe even in sets. And I have an action of a group G. And I can always just consider the fixed points. And I've given this talk to undergrad, so I even defined the fixed points, but it's like all of the points that are fixed by every element in H. And there's just some natural maps that you have just because there's fixed points, right? So like if you have K as a group of H, you have an inclusion of the H fixed points in the K fixed points. And that's just because if you're fixed by everything in H, you're fixed by everything in K. And then there's like a conjugation homeomorphism that's going on. But then if in addition, my set has a G commutative monoid structure, and you could mean two different things by that. So I have a G action on a commutative monoid, or I have a commutative monoid structure in the land of G spaces, and actually those things mean the same thing. But it is what you think it means, that like my G action is via monoid maps. Then this is where I get the wrong way maps. And here I'm just not doing anything up to homotopy, but when I'm doing things not up to homotopy, I get this wrong way maps. And just to give you an example, again, I give this talk to undergrads. The beginning of the talk I give to undergrads. You really need commutativity for that. So if you're looking at this formula here I have an element. So here's my map from X to the fixed points just takes X and sends it to the sum over the orbit. And if I take any other element of the group and I do the action, when I first pass through the sum, I get the same summons, but in a different order. So it's really the commutativity of the monoid structure that allows me to say that I have the wrong way map. Without commutativity, I don't have that wrong way map. And I really want you to remember this, because when we say, oh, well, when I have a G-commutative monoid structure, maybe I get some wrong way maps, it's coming from the fact that it is the commutativity that allows you to write those wrong way maps in the strict setting when you don't have things apt to homotopy. So when we want to define G-commutative apt to homotopy, we realize we have choices, and this is the work of Blomberg and Hill. So you make some choices, and the first choice is that maybe I'm going to decide that I have an E-infinity structure underlying the whole thing. So in today's talk and throughout what Mike has been telling us, we've always considered kind of like that the underlying structure, if I forget about the G action, is E-infinity. And there's very interesting questions if you decide not to go to E-infinity there, and there's people actively working in those questions right now. But even when you've decided that you have this E-infinity structure underlying, there's choices, and the choices live between the place where you have no transfers whatsoever and the place where you have all the transfers, but there's things in between. And this is the story of an infinity operads that Mike has been telling us throughout the week. And one important thing to note, though, is that the existence of some transfers implies the existence of others. And the very easy one to see is that if you have three subgroups that are nested, if you have the transfer from XL to XK and the transfer from XK to XH, well, that's going to induce a transfer for the composite. So this is the most basic one that I could write, but this is why when in a couple of pages I define transfer systems, there's going to be some compatibility conditions that are going to show up. So we've seen this definition at least once this week, the definition of an N-infinity operad, which is by Blomberg and Hill. But I'm going to repeat it anyway. So an N-infinity operad is an operad in the category of topological spaces with a G action, where the sigma in action is going to be free at every level. And then I'm going to ask for this condition on the subgroups of G cross sigma n, that is that the fixed points are either empty or contractible. Now, if you remember from Mike's talk, he actually had a condition that you only were looking at the gammas that had a trivial intersection with sigma n, but I'm actually taking care of that by saying that my action is sigma n free. And then I have this extra condition that says that when I take the whole group G, my fixed points are non-empty. And then I'm going to define, I'm going to say that a map of an infinity operads is a weak equivalence if it's an equivalence on fixed points for this gadget. So really, I should be thinking that the fixed points are the things that are controlling everything that I'm doing here. And then these conditions imply that we do have an infinity operad when we forget about the G action. So forget everything related to G, and then the underlying operad is an infinity operad in the usual sense. And then the gamma fixed points are encoding transverse maps. And this is something that Mike spent a lot of time telling us in the first couple of days, but I actually wanted to give you a perspective that I find very helpful when I talk about this. And I'm going to go into a little bit of detail here. So imagine that I'm taking K as subgroup of H of index N, and I'm going to take a graph subgroup for this H mod K as an H set, and I have to give it an order so I can think about it as a representation. So I have a group homomorphism from H into sigma n, and then that's going to give me, when I look at the graph of that, I get this graph subgroup. So this is one of the ways in which we can build some of these subgroups of G cross sigma n is if you have an H set, then you just look at a permutation representation for that. And notice that this actually requires a choice of ordering the elements of the in this case of the coset. And so if you give me an O algebra, just the definition of having an O algebra says that I have a G cross sigma n map from O of n to the mapping space of xn into x. That's just what it means to be an O algebra. And if I take the gamma fixed points, then I get this piece of the map. And it turns out that you can very explicitly, and I'm not going to do it today, but very explicitly write a function from the, so notice that, what is this? So this thing here is all maps from extending to x with the g action being given by conjugation, and then I'm taking the gamma fixed points. And very explicitly, you can write a function from that into the mapping space from xk into xh. And you can actually, as I said, do this very, very explicitly. But overall, that tells you that if this is non-empty, then you get a transfer. And so the structure of being an O algebra gives you this transfer maps in the wrong direction. And that this is one of the ways in which you're getting them encoded. So jumping to the definition of transfer systems, and I'll circle back to an infinity operads in just a second. I'm going to let sub G denote the lattice of subgroups of G. And I'm going to define a transfer system on G just to be a relation in this collection of subgroups, which is a partial order. And if you don't know, that means that it's reflexive and transitive. And it refines the usual inclusion. And that's just like what other people have said, like if you have the relation, it means that you had the inclusion. You cannot have the relation if you didn't have the inclusion of subgroups. And then it's close under conjugation. And then there's this picture of being close under restriction. And people have already talked about this. So I'm not going to dwell too much on this today. But then you can actually look at the whole collection of transfer systems. And this is actually a poset itself, because you can actually include you can ask yourself if one transfer system includes in another. I love looking at examples, and I love this example in particular. So if your group is CP, where P is some prime, then the collection of subgroups just looks like this. You just have the trivial subgroup and then the whole group. And then you have two possible transfer systems, which you can see this way. This one here is what's called the trivial transfer system. It doesn't have any non-trivial transfers. And this one is the complete one. And that's all you get in this case. But if you move on to CP squared, now this is what the collection of subgroups looks like. You have three of them, and they're all nested in each other. And you can ask yourself, well, what does it mean to be a transfer system? And rather than give you an exercise, which would probably be a better idea, I'm just going to tell you the answer. So transitivity, there's just one interesting version of transitivity, which is that if you have these two, then you have to have the long one. And then the restriction one is just that if you have the long one, you have to have the bottom one. Those are the two conditions that are interesting. And then you sit down for a while. You can even give this exercise to your undergrads, and then they come up with this 5 possible transfer systems on CP squared, and they're actually neatly organized into a pentagon. And then maybe you give them a little bit more time, or you go and read this really cool paper by people who are here. So theorem of Balchin, Barnes, and Rothheim is that the number of transfer systems of CP to the n is the n plus first Catalan number. And they actually organize into what's called by the combinatorialists the Tamari lattice, but we homotopy theories maybe think more of the associahedron and the edges of the associahedron. And so this result is what got me into this business, because Kyle Ormsby and I work at a 4-year liberal arts college in the US. And we were looking for something to do with undergrads, and we heard about it, and we said, oh yes, we can give this to undergrads and they can do cool things with that. This is not the talk in which I'm going to tell you about the cool work that our undergrads have done in this area of transfer systems. I'm happy to tell you more outside of the talk, but just to let you know that this is the kind of thing that like you can get undergrads to work on, and this is why many of us are kind of have been looped into this story. But going back to an infinity operads, there's a reason why transfer systems were defined. So again, we heard about this from Mike. The theorem, one of the theorems in Blomberg-Hill is that if you give me an infinity operad, you can define a relation by saying that K is related to H, if and only if K is a subgroup of H, and the corresponding fixed points are non-empty. So here I'm using the same notation as before, where there's some graph subgroup associated to the H set H mod K, and you can just look at the fixed points and ask, is it empty or not? And that's going to give you a relation, and that's going to give you a transfer system. And I'm being a little bit ahistorical here because Mike and Andrew really wrote this in terms of like indexing systems, and then it was work of Jonathan Rubin and Balchin, Barnes, and Reutzheim to translate it to like this business of transfer systems that we really only need to look at the subgroups because they're really encoding all the information that you need. And then there's the sort of like nice converse. So you can build a functor from the category of n infinity G operads with this weak equivalences that I mentioned before. And so there's a functor, and this is giving you a little bit more information that we have here, because saying that there's a functor is also telling you something about when there's a map, you have the relation of inclusion here in the world of transfer systems. And more importantly, this induces an equivalence. So Blomberg and Hill had proved that this is that the functor exists and is fully faithful, but then you actually needed to prove that it's essentially surjective, and this is independent work of this group of people. And if you actually think about this, and this is going to be relevant to what I'm going to tell you in a bit, proving the converse actually means building explicit n infinity operads giving a transfer system. And anyone who has tried to build operads knows that sometimes that's not easy, right? And so these people do it in very, very different ways. And in particular, the one that I'm the most familiar with is the work of Jonathan Rubin, where he constructs a free operand in a very specific way and making sure that it does the right thing and it contains the right kind of transfers. Now, moving on, and this is again a story that Mike has told us, there's the story of buying complete Tambara functors and compatible pairs. And it all starts with like the observation that if you have an infinity operand and you take an algebra in G spaces, then when you take the connected components and think about it as some sort of Mackey functor, you don't get a full Mackey functor, you get an incomplete Mackey functor, meaning that you only really get some transfers, not all. And which transfers are you getting? Well, surprise, surprise, you're getting the ones that are being encoded by your operand O. Meaning the ones that are being recorded by the corresponding transfer system. And similarly, if X is an O algebra in genuine G spectra, again, you look at the connected components, and this is not going to be a full Tambara functor, it's only going to be an incomplete one where you have some of the norms, but not all. And which norms do you have? The ones that are being encoded by O. So they use this kind of like as a motivation for what they define to be by incomplete Tambara functors, which are sort of like Tambara functors, but they don't have all their norms, they don't have all the transfers. And as you do this, you discover that the existence of certain norms implies the existence of certain transfers, just like having, and maybe this shouldn't be surprised because after all, norms are multiplicative and transfers are additive. And in order to talk about certain things about multiplication, you need addition. Right? So that is kind of like why maybe you shouldn't be surprised about this, that like the existence of multiplicative structure implies existence of additive structure. And so I have this as a theorem of Blomberg, Hill, and David Chen, which is that you can actually give necessary and sufficient conditions for this kind of compatibility to happen. And so if you give me a pair of transfer systems, and here I'm calling them suggestively TM for multiplication and TA for addition, the theorem is that this encodes the norm transfers of a bi-incomplete Tambara functor if and only if you have an inclusion of the multiplicative one in the additive one. And then there's this condition, which we had seen in Mike's slides before. And it's just like a very explicit condition, like if you have this one is additive and this one is multiplicative and this one is multiplicative, then this one must be additive. There's also a translation of this in terms of indexing systems, which I have here because it will be helpful for me in a bit. In terms of indexing systems, the condition is that if you have H mod K in TM, and I'm putting in quotation marks because now I'm being not careful about the translation between transfer systems and indexing systems. But when I say this, I really mean the associated indexing system. So if I have H mod K in TM, and if X is a K set in the additive piece, then you must have the co-induced H set must be in TA. And that's the only condition that you need in order for you to have compatibility between the multiplicative part and the additive part. And we're just gonna give them a name, we're gonna call it a compatible. So just very briefly, a different version of this talk, I would talk about this joint work with Kristen Mazur, Constance Rotheim, who's here, Rebecca Santana, who's here, Danica Vanille, who's here, and Valentina Zapata-Castor, who's not here. And where we study compatible pairs for groups of the form CP to the R, Q to the S. Danica told us all about it, so I don't have to tell you anything about it, other than it's pretty cool work. And actually, maybe I should say, Mike Hill has some work with undergrads where they study compatible pairs for the group CP to the N, and they actually get a full count, which is amazing. But I'm not going to tell you about this. I'm going to tell you about other work with another group of people. So this is where maybe this talk should really be titled "Realizing Compatible Pairs." And so this is joined with David and Myung-Sing and Pablo and Paula and Ben. This is my team from the MRC. So I feel like we've been throwing out this MRC words for a while. Maybe some of you don't know. So last summer we had this workshop organized by the AMS, or put together by AMS, organized by a bunch of us, where it was a collaborative workshop doing work related to transfer systems. And so we had this question, which is, well, the definition of compatible pairs is completely algebraic. It's coming from looking at buying complete type bar functors. And then you might ask yourself, well, is there an operatic interpretation? After all, transfer systems are coming from operads, right? So can we actually give an algebraic interpretation to this? And there's different ways of rephrasing the question, but I'm going to rephrase it in terms of operad pairs. So here I'm following some work from Peter May in the 70s and 80s. So I'm in some symmetric monadal category, and I have two operads in there. And I'm going to say that I have an action of P on Q. If I have maps like this, so the map is going to go from P of K, tensor or smash or times, depending on whatever category you're in, Q of J1 dot 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 Q of JK, and goes into not the sum but the product of the J's. And this is different than having kind of like a module structure in the usual sense, because instead of going to the sum, I'm going to the product. And you should really be thinking that there's something about multiplication happening in here, because I'm multiplying instead of adding. And satisfying some conditions. And this is just, I mean, in the world of operads, the list of axioms is long and nasty and involves like some equivariance with respect to the symmetric groups that are hard to keep track of, and you need to be careful about. And the idea, or like why Peter was interested in this, is that if you have an action of P on Q, you can actually, in a very, very precise sense that I'm not going to tell you here, you can make sense of what it means to have P algebras in the land of Q algebras. And what I mean by that is that really you have kind of like an additive Q structure, and then P is giving you a multiplicative structure in the sense that those multiplicative maps distribute appropriately over the Q maps. And that's the idea. So this is a little bit different than what Natalie was talking about, where like it's two actions that kind of commute over each other. This one is one distributes over the other one. So really, I should be thinking about kind of like ring-like objects where P is giving me the multiplicative structure and Q is giving me the additive structure. So I can rephrase my question into two questions, two now very concrete questions. The first question is, if you give me two and infinity operads and P acts over Q, when I look at the associated pair of transfer system, is it compatible in the sense of Chan and Blumberg-Hill? And that's a very concrete question in one direction. It's kind of saying, well, are we seeing the same notion of compatibility when we're looking at this kind of operatic action, which is supposed to be talking about P being multiplicative over Q being additive? And then the harder question is, if you give me a compatible pair of transfer systems, can I actually realize this as a pair of two explicit operads, P and Q, which have the correct transfers and I have the action? So if you think about it, this question too should be really hard because it has to do with constructing operads that do something for you. So it's kind of like, it's trying to do the backwards part of the big theorem from before, but now in addition, keeping in mind the multiplicative structure. So maybe a little bit ambitious to try to do this in a week. But well, we're still not done. You'll see soon. So I do have a theorem for the forward part. Unfortunately, this acronym is not pronounceable in the other way that some of my other acronyms like BOR are pronounceable. So I'm just gonna have there a lot of last names, a lot of letters. But we did prove that if you have your operads and you have the action, then you get a compatible pair. At least the thing that we were hoping to be true initially for the easy version of the question is true. And I feel like every talk should have at least a sketch of a proof, and this is as much as you're gonna get as a sketch of a proof from me today. So I need to prove, following the definition of compatibility, that if HK is being encoded by P, and I have some K set X, which is encoded by Q, then the co-induced set, the mapping space from H to K as a K set, this is needs to be in Q. So very explicit things once I translate into graphs of groups. So here, maybe I need to start doing some specific choices where I'm gonna let N be the index of K and H, and I'm gonna let M be the cardinality of X. And so our assumptions actually are saying that these fixed points are non-empty. And this fixed points are non-empty, so I can take some elements in there. And what I need to prove is that over here, some fixed points are non-empty. So you just take your multiplication map, or like your action map, you do something where you take your B in here and actually act by elements of H, but which elements you need to choose some coset representatives, all the things that they tell you shouldn't do. Here you have to make all these choices, but it's because you're looking for a specific set of fixed points here, not being non-empty. And you just take this multiplication, all of the cardinalities work out the right way, and you just prove that this is a fixed point with respect to the appropriate thing. Now, this is not hard to do, it's just extremely painful because you have to keep track of a lot of things, but it turns out that it is true. And if you're stuck in a room in somewhere in upstate New York for a while, then it turns out that you can do this. Yeah. For the people who are there, I know you remember all the post-it boards in a room with many things. Yeah, Maria.
So in the group, in some sense, you don't use the whole structure of acting.
Yeah, part of it is because thanks to the work of Mike and Andrew, they've really kind of collapsed the whole notion of compatibility into just checking this very simple thing. But if you actually like look at the initial thing that it requires to have the compatibility in terms of like which transfers are needed in terms of the norms that you have, then you initially think that maybe you should have to look for a lot more. And part of what's going on is that in Operads, because you have within a single operad, you have relationships that are vertical, right? Because like you can, for example, if I take a single element, I can take the multiplication of it with itself a bunch of times by some other operation, right? So this kind of like vertical relationship in the operad tells you that you don't really have to check everything, you just need to check some piece. And in the end, this is all you have to check, but it doesn't mean that like there's not other pieces that are fixed points with respect to other subgroups that are not empty. Those are just implied by these ones, and these are the smallest ones that we need to check. But I think your question is interesting because when I'm going the other way around and I'm trying to build an operad, I actually need to build a lot more things, and this is where like things get tricky. So it turns out that in general, finding operad pairs of like two pairs of operads that activate over each other is actually not that easy. But there's a very canonical pair that has been around for a while, sometime in the 70s, which is the linear isometries operad and the Steiner operad. We've actually heard about these two earlier this week. Here I'm not equivariant for a second, and the linear isometries operad is just looking at level n at linear isometric embeddings for n copies of R infinity to R infinity. And then we also have the Steiner operad, which I was actually looking at Steiner's paper, and he in the very, very short introduction to this paper, he actually talks about that like he came up with this operad in part so that there could be a pair of operads that one acts over the other one. So the Steiner operad is kind of like little disks, but not quite, because instead of just looking at embeddings from R infinity to R infinity, which is what little disk would be, you're looking at paths in the space of embeddings, and they're paths so that at 0, you have a little disks, basically. So if you were to just restrict at t equal to 0, you're looking at a little disk operad, but then you actually have these paths that start at a little disk, and then for each of the paths in the end, you get the identity. So this is a picture of sort of like what happens. I mean, this is where if you were just doing R1 instead of R infinity, where like you start at time 0, you have these joint images, and then as time goes by, maybe like they start getting bigger, and in the end, both of them are the identity. But the Steiner operad is actually it's very nice in part because it's like little disks, but it actually fixes some of the issues with little disks in terms of being able to take limits as your vector spaces get larger in dimension, but also it has like this nice property that you do have the action. And I think, yeah, I'm telling you what the action is, although I don't want to dwell too much on it. This is probably the most technical slide in the talk. There's actually an action of L and K, and the idea is the following. So if you have, this is a linear isometric embedding, and then you have this H1 through Hn, but actually remember that H1 is actually a J1 tuple of paths in the space of embeddings, and the same is true for this one. And then somehow I need to give you a J1 through Jn tuple of paths in the space of embeddings. Now, I'm going to fix the path thing by just like telling you what happens at a given t. And one thing that I can do to deal with the fact that this is like J1 times J2 times Jn is to think of this really as like taking the product of the set J1, which is the set of elements from 1 through J1, and so on up to Jn. And so really thinking that an index in here is the same as a tuple of indexes in here, and that I have to make a choice and do, let's say, graphical ordering, and this works out. And so what this lambda does is that it takes this f and this h1 through hn, and it takes the inverse of f, Then I have here n coordinates, which means that I can take the sum over n of these things. And so what am I doing here is for each of these i's, which is from 1 through n, I take the alpha I coordinate of this h1 or the alpha 1, and then I look at the value at t, and that's just going to be an embedding from R infinity to R infinity. As I take the direct sum of all of those, I get this map from R infinity n to R infinity n, and then I compose with that. So you can sort of like think about this one as letting me go from n copies of R infinity to R, and then in each of the copies, I do what this one is telling me to do. And it turns out that this works out, and you get your operad action. And notice that the T there is just for the right. So I didn't need the actual Steiner piece to do this as long as I had my embeddings working appropriately. So there are equivariant versions of linear isometries and Steiner operads. We've heard about them this week, where you replace R infinity with some universe U, and all of this works out equivariantly all right. Which, if you take that for granted, it actually tells you that you have realizability for these pairs of compatible transfer systems. And as I'm reading this, I realize that like I'm being somewhat vague about what I mean by these pairs. But if you remember from Mike's talk, if I have a universe U, and I should have said this before, the Steiner operad is actually equivalent to little disk operad. So if you start with any universe, any G universe U, you have the associated disk operad or Steiner operad, and you have the associated linear isometries, and these actually don't have the same collection of transfers. This was one of like the main things that like you guys have like something weird is going on. So doing this pairing equivariantly gives you a realizability kind of theorem for any pair of transfer systems where you're dealing with the same universe and you're dealing with the disk-like piece of the universe and the Steiner, the linear isometries versions of the universe. But that's all you get from this. Now, in order to tell you a partial answer to the more broader question that we came up, I have to tell you about a sort of silly but pretty useful construction that you can do with operads. So if you start with any operad in set, where sigma n acts freely on O of n, and look here that I really started with just an operad in set, and all I'm asking is to have a sigma n action on it. And maybe my favorite example of this, is the associative operad, right? I could start with this if I wanted. Then what I'm gonna do is I'm gonna take the functor that those functions from G as a set into O. Because that's a functor that preserves products, I get an operad in G sets. So the elements of these operad at level n are just set functions from G into O of n. But that still has a sigma n free action. And then I'm going to do something that again seems a little bit silly, but it's pretty useful, which is that there's this functor from set into simplicial set. And then maybe I'm going to take the nerve to go into topological spaces, where I take a set and I send it to the simplicial set that is at level n is n plus 1 copies of x. If you actually think about this, and so what are going to be my phases and degeneracies? They're just going to be diagonals and they're going to be projections. Well, because of this n plus 1, this actually has an extra degeneracy, which tells me that this is contractible. No matter what x I bring in, it's contractible. So this is a functorial way to produce a topological space that is always contractible. But then, for example, my free sigma in action, I still have it here. So where actually when you do this to this operad, the associative operad, that's when you get the Barrett-Eccles operad. Now, for those of you who know me, I tried really hard to not think about this as a categorical construction that I would do instead, which is I start with a set and I build a category that has exactly one morphism between any two objects. And then if I take the classifying space, I'm doing exactly the same thing here. So if I start with my operad G, I can define something also O sub G, where I did this whole construction. So first I started with O, then I looked at functions from G into O, and then I did this E construction. And it turns out that that's an operad in G top, and it's actually not too hard to show that this is indeed G E infinity. So it's N infinity for all transfers. So it seems like a very silly construction, but because I had this free sigma action and I kind of like added the G kind of like by doing this kind of toe induction, it turns out that this has all the transfers. So you can do this to the linear isometries operad and to the Steiner operad. And one thing that I really want to emphasize here is that it's something very, very silly, because the linear isometries and the Steiner operad, they have a topology that is interesting, and like that topology is what leads you to prove that they're contractible in the appropriate sense. But here we're actually forgetting about that topology. And then we're building a new thing that's contractible just by doing this like construction here. Now, why are we doing this? Well, because it's really hard to come up with operad pairs in general, and we have something that has an operad pair already. And all of this construction is functorial and it preserves products, which means that it preserves operad pairs, right? Like, so these two, and I don't have it here, but I'm gonna write it, and LG acts on KG. Just for free, because we just took something, the word that was an action, and then we did this functor that preserved products, and then everything was fine.
Can you remind me why we're doing this? So why couldn't we just look at maps G into 4, and why do we have to do this E?
Oh, because that's not gonna be contractible anymore. And also, and moreover, I not only need that to be contractible, I need, so when I'm saying this statement here, that this is G infinity, I want to make sure that when I take fixed points with respect to any graph subgroup, I get that it's either empty or contractible, and that's not going to be true if I just stop here. Yeah. And maybe another thing to say about this is that this is very different than just taking an equivariant universe and doing linear isometries or Steiner with the equivariant universe. We're just taking the trivial universe, and then we're building the G action by doing this. So here's a theorem, and I apologize to Ben, I really don't know how to pronounce his last name, Mike.
Testing.
Thank you. So this is a theorem about Chesney, which says that if I have a transfer system, then I can actually pick a suboperad of LG that has the right transfers, and I can pick a suboperad of the Steiner operad that has the right transfers. And you should think about this and think that like this is very a non-trivial statement, and that is actually very hard to prove. If I tell you a little bit of the history, there were, when the problem of building operads for a given transfer system was open, some people were trying to prove it in this way with the Barrett-Eccles operad. And it turns out that you can actually prove that there's some transfer systems for which no suboperad of the Barrett-Eccles operad will have the right transfers. And part of what's going on is that maybe you say, okay, I want to have the subgroups being non-empty, so I'm going to make sure that I include some elements that have the right isotropy group. But then when you take the suboperad generated by those things, you're actually maybe throwing in more things that have isotropy groups that you didn't want to include. So the process of getting a suboperad with the right thing is non-trivial. And so this is actually a pretty big deal. And in a way, it gives another proof of that equivalence of N infinity and transfer systems, because it gives a different way of building operads with the right thing. And the way that Ben is doing this is not by taking some elements and then taking the suboperad generated by it, but instead what he's doing is picking some elements that have the right isotropy groups and then proving that they were closed under the Operads structure. So instead of building a generated suboperad, it's taking something and proving that it's a suboperad, and this is why this actually works. Using this theorem of Ben, then we can prove that, well, actually, now I have here what I had said before, that we have an action of LG on AK, and then we can just restrict that action to the suboperad LT, and we get an action of LT on KG. And if you think about this long enough, you realize that maybe I'm not saying something too deep, because I'm not restricting to a suboperad here, so I don't have any problems with where I'm landing when I do my operad action. But the option of this is that we get that if you give me operad pairs where you have any transfer system and the complete transfer system, those are realizable always. So I don't have to I don't have to just be looking at this and linear isometries ones. I always get this for any complete. And maybe something that I should say is that this pair is always compatible, because my compatibility is if something needs to be here. So that's one of the ones that Danica had told us about, is that's one of the ones that is always there. Oh, I realized that these two are the same. Right, I was probably trying to do more when I was creating this. Now, here's our hope, and this is the part where I say we, but I really mean them. While I'm busy with stuff at work and kids, trying to prove that the more general statement, trying to prove that if you give me any compatible pair, you do have the action. And here, the tricky thing is to kind of prove that with the definitions of the operads that Ben has given us, to make sure that if you're trying to restrict the action that you have of LG and KG, that you're landing in the right place. And that's hard. So that's the current state of the project, and we're hopeful, but maybe there's more work that needs to be done in terms of that. And that's actually everything I have to tell you. So thank you.
Part of the theorem that the Steiner operad for a given, that the isometries operad for a given universe acts in the Steiner's operad, or vice versa. Isometries. Okay, yeah. So I'm wondering if I fix an operad and look at the interval in the transfer lattice of transfer systems / operads that act upon it, are those questions you've reconsidered at all? I mean, I guess it's hinting at my talk in an hour, but what the maximal one that might operate on it is?
No, we haven't thought about that.
Okay.
Yeah, and yeah, that's probably all I should say.
Cool.
So there were some questions that you couldn't get answered. Would you like to speculate about them?
So I think, well, there should be a way of constructing sort of of realizing every compatible pair, but I don't know if this method is necessarily going to be the one that works. But there's also just some of this project requires sitting down for 5 hours at a time to figure out whether something has the right the right isotropy group, and we just haven't had that time to do that.
The other, the other question that you gave well, it's on the board now, the explicit, one explicit action on the other, I mean, how hard is it to construct actions?
It's really hard. So one of the things that we tried earlier was using the explicit construction of Jonathan Rubin to like, so he has a very, very explicit construction of the n infinity operads, and it's free in a sense. So like maybe your hope that because it's free in a sense, like you just have to tell you where the free things go. But it turns out that when you're doing these multiplicative structures, the freeness in L helps, but the freeness in K doesn't help you at all. So you actually want to hope to be able to like tell you where the like lambda sending things, but then you have to make explicit choices, and then the whole thing just like gets very complicated.
So I'm not as familiar with this operad pair or operad action stuff. But you said the motivation was like trying to find a way to talk about like P algebras and O algebras, right? Subject to distributivity rather than interchange. How different is this from like, say, the construction that Mike was talking about, where you just by hand construct these indexed box products and norms and whatnot on Mackey functors directly and just evaluate P algebras separately?
I mean, this is very different, right? It's like a parametrized versus non-parametrized version of thinking about things. And I mean, this is, again, we kind of chose to answer the question of realizability in this very specific way, but that doesn't mean that there's not other ways in which you can ask a question of realizability.
Your results are for a general finding sheet?
Yeah,
Do you, yeah, I'm sorry, what were you?
go ahead. Yeah, there's no abelian, for example.
Yeah, well, that was gonna be my question, is like, I wonder, like, do y'all have a sense as to if, like, assuming abelian or assuming cyclic could like make some of these things more approachable, or does it just seem also incredibly hard that it's like, might as well hit them all at once?
Yeah, I mean, I think there's something to say that like, if you maybe look at a specific group at a time and you have a very, very small collection of transfer systems, maybe you can do a very explicit construction. But the way that we are approaching it, it just seems easier to just do an arbitrary finite group G.
Do you have a good intuition for how to think about this lambda map in the operad pairs? Because at least in my mind, I'm like, okay, there's a multiplication and then a bunch of additions, and you want to think about composing those sort of. But then on the right hand side, you only have an addition, right? So where did the multiplication go?
Well, the multiplication put together your additions, right? Like, so like the idea is that multiplication is repeated addition. Right? And so you have a bunch of additions and you're putting them together, but that's just an addition. Maybe it's easier to think about it if n is 2. And then maybe the other ones are still 2, and like you're just kind of like thinking about the distributivity.
Thing. Yeah.